Hello friends, I am Mahaveer Chougala, Assistant Professor in Department of Electronics and Communication, Jain College of Engineering, Belagavi. Friends, in the today's lecture, let us begin the third module in signal and system, that is system properties of LTI systems in terms of impulse response. And in this lecture number 1, we are going to cover up the interconnection of systems, mainly LTI systems, and the system properties of LTI systems in terms of impulse response. And then lastly, we are going to cover the step response of LTI system. So today, in this lecture, let us understand what do you mean by impulse response and what is the interconnection of these LTI systems. So basically, impulse response is nothing but it is the output or response of the system, and the input is the unit impulse function or delta function. When the input to the system is impulse function, then the output is known as impulse response, that is h of t. Right? So now we'll understand what do you mean by the system interconnection. So in this concept, the two or more LTI systems are connected in two fashion, that is configuration, either in series or cascaded or in parallel fashion. In the first case, we have the two systems. You can observe here, the two systems are connected in cascade, right? So these two blocks represents the LTI systems having the impulse responses. So the first LTI system is having impulse response h1 of t, and second system is having impulse response h2 of t, and both the systems are connected in series or cascade with input x of t and output y of t. So whenever the two systems are connected in series, what is the overall system response? That is impulse response. The overall impulse response is given by h1 of t convolution with h2 of t. Please remember, when two systems are connected in series, their overall impulse response is given by h1 of t convolution with h2 of t. And the relation between output and input of the system with the overall impulse response is given by y of t is equal to the input x of t convolution with the impulse response h of t. But h of t is the overall impulse response which is given by h1 of t convolution with h2 of t. So therefore, the output y of t is equal to x of t convolution with h1 of t convolution h2 of t. Right? So in the second case, you can observe here the two systems are connected in parallel. h1 of t is one LTI system, the h2 of t is corresponds to impulse response of the another LTI system, and both are connected in parallel, and their output is summed using summer or summing element. So here the overall response is given by h1 of t plus h2 of t, and the input is x of t, output is y of t. So as we know that the output of any system y of t is the convolution between the input x of t and its impulse response. So y of t is equal to x of t into the overall impulse response when two systems are connected in parallel is h1 of t plus h2 of t. So these are the two configurations where the systems are interconnected. One is the series configuration and another one is the parallel configuration. So now let us see some examples where you will be given some block diagram in terms of system impulse responses as well as input and output. You have to find or determine the overall response in terms of the impulse responses of each subsystem. I mean, you have to find the overall response of the system in terms of the impulse responses of these subsystems. Now, see here, the H1 of t is connected to the two systems having impulse responses H2 of t and H3 of t, and which are connected in parallel. So now let us simplify or determine the overall response of these two systems connected in parallel. So H2 of t is connected with H3 of t, so their overall response will be H2 of t plus H3 of t. And this overall response is again connected in series with another system having impulse response H1 of t. So now this H1 of t is connected in series with this H2 of t plus H3 of t. So now when these two are connected in series, the overall response of these two subsystems is given by H1 of t convolution. Please remember, these two are connected in series. That's why it is convolution. H1 of t convoluted with H2 of t plus H3 of t with input x of t, output y of t. Now again you can express the output y of t in terms of the input x of t and overall impulse response h of t, that is nothing but h1 of t convoluted with h2 of t plus h3 of t. So the overall response is h of t is equal to h1 of t convoluted with h2 of t plus h3 of t. So we have another example here where the h1 of t and h2 of t are connected in series here, and h3 of t and h4 of t they are connected in parallel. So now let us simplify the systems which are connected in series. So h1 of t and h2 of t, since they are connected in series, their overall response will be h1 of t convoluted with h2 of t. And coming to here, h3 of t and h4 of t, they are connected in parallel. So their overall response will be h3 of t plus h4 of t. And now these two overall responses are again connected in parallel. But see here, the sign of this summer is different. Here it is not plus plus, it is plus minus. So therefore, the overall response of these two responses is given by h1 of t convoluted with h2 of t minus, because here it is lower sign of this summer will be is minus, so it is minus h3 of t plus h4 of t with input x of t and here this response is connected with another system which is in series with this overall response, that is h pi of t. So the overall response is given by h1 of t convoluted with h2 of t minus h3 of t plus h4 of t convolution with this h pi of t, because this is in series with this one. So the overall response will be this one, h1 of t convoluted with h2 of t minus h3 of t plus h4 of t into, that is convolution with h pi of t, right? So in the example 3 here, it is exactly a different example. It is exactly a reverse case of the previous example. In the previous case, you will be having some block diagram representation and you are asked to determine the overall impulse response. But in the example 3, you will be given with the overall impulse response of the LTI system H of t, and you have to draw the block diagram. That is block diagram which represents input, output, and impulse response. So here at the left side we have input, and right side there will be output y of t, and in between there should be the overall impulse response of the system, and that is given in the problem statement by h of t is equal to h1 of t convolution inside the flower bracket h2 of t plus h3 of t plus h4 of t. Means you see inside the flower bracket it is a sum of three impulse responses. That means these systems are connected in parallel, and these systems are again connected in series with the first system of response h1 of t. So now first let us connect these three h2 of 3, h3 of t, and h4 of t in parallel, and then these parallelly connected systems are connected with h1 of t in series, and the input is x of t and y of t. This is a very simple to draw the block diagram whenever the overall response of the LTI system is given. So once we understand the interconnection of LTI system, there are three important properties of LTI system in terms of their impulse response, either h of t or h of n. So now the first property we'll discuss, that is memoryless system, and we know that what are memoryless systems, as we already studied in the system properties. Any system or a system is memoryless if its output at any time depends only on the present value of the input. And this is true for both discrete time LTI system as well as continuous time LTI system. Means the present output depends on only the present input. That is, h of n is equal to 0 for n is not equal to 0 for a discrete time system. So these are the very important two conditions to say the system is memoryless, right? H of n should be 0 for n is not equal to 0. Means h of n should not have any value other than n is not equal to 0. Similarly, h of t is equal to 0 for t is not equal to 0. For example, if I take delta of n, the delta of n is equal to 1 only at n is equal to 0. For n is not equal to 0, delta of n is not equal to 1, it is 0. That's why delta of n is a memoryless system. Similarly, delta of t for continuous time system. So please understand, a system is said to be memoryless if its impulse response h of n should be 0 for n is not equal to 0 in case of discrete time system, and in case of continuous time system the impulse response h of t should be 0 for t is not equal to 0. So you'll understand these two conditions when we discuss a few examples, right? So here, the first example, the impulse response h of t is given, that is equal to 5 times delta of t. So we have to verify whether the system with this impulse response is memoryless system or not, right? And we know that the delta of t is equal to 1 only at t is equal to 0, and other than t is equal to 0, that is t is not equal to 0, delta of t is equal to what? 0. So when t is equal to 0, delta of t is equal to 1, so 1 into 5 is equal to 5. When t is not equal to 0, delta of t is equal to 0, so 0 into 5 is 0. So now you can observe here, h of t is equal to 5 for t is equal to 0, and h of t is equal to 0, t is not equal to 0, right? So the condition is satisfied, right? Whatever the condition we have here, that is h of t is equal to 0 for t is not equal to 0. So we have h of t is equal to 0 when t is not equal to 0. So you can say the system is memoryless. So another example we have here, that is h of t is equal to e raised to minus 2t. It is an exponential decaying function which is multiplied by the shifted version, time shifted version of the unit step function, right? That is u of t minus 3, right? Now, the u of t minus 3 is given by u of t minus 3 is equal to 1 from t is equal to 3 to infinity, because u of t is equal to 1 from t is equal to 0 to infinity. U of t minus 3 means it is right shifted by 3, so the t varies from 3 to infinity, right? And at t is equal to 0, at t is equal to 0, we have u of t minus 3 is equal to 0, right? So at t is equal to 0, we have u of t minus 3 is equal to 0, so h of t is also equal to what? 0, right? And when t is not equal to 0, when t is not equal to 0, u of t minus 3 has some value that is equal to 1, and that 1 is multiplied with what? E raised to minus 2t. Therefore, when t is not equal to 0, h of t will not be 0. That's why this system is non-memoryless, or it has a memory. And the memory systems are also known as the dynamic systems, whereas memoryless systems are known as static systems. And coming to the second properties of the system, that is causal system, and we know that a system is said to be causal system if its output depends only on the present or the past values of the input. And in terms of impulse response, for a discrete time LTI system to be a causal system, if h of n is equal to 0 for n is less than 0, means any discrete time LTI system is said to be causal if its impulse response h of n should be 0 for n is less than 0. And similarly, for continuous time LTI system is said to be causal if its impulse response h of t should be 0 for t less than 0. So now let us understand with two examples how to determine whether the system is causal or non-causal. So the first example, the impulse response h of t is equal to 3 times delta of t again. And we know that since delta of t is equal to 0 for t is less than 0, right? Therefore, when delta of t is equal to 0 for t is less than 0, obviously h of t, because it is 3 times delta of 3. So when delta of t is 0 for t is less than 0, h of t is also 0 for t is less than 0. So when h of t is equal to 0 for t is less than 0, the system is always a causal system. And in the second example, it is a discrete impulse response h of n, which is 1 by 2 raised to n u of n. And again, look at this u of n, which is discrete unit step function u of n. And this u of n is equal to 0 for n is less than 0, because u of n is defined only for positive values of n, that is 0 to infinity. For negative values of n, u of n is equal to 0. And when u of n is equal to 0 for negative values of n, the h of n is also 0 for negative values of n, that is n is equal to 0. Therefore, this system is also a causal system. In the next lecture or video, we will be discussing more examples on these system properties. And the one more system property we have is the stable system. Any system is said to be stable if every bounded input produces a bounded output. So bounded input means the finite input, right? So for every finite input, if system produces the finite output, that is bounded output, then the system is considered as the stable system. Otherwise, it is unstable, right? A stable system. So a discrete time LTI system is stable only if its impulse response is absolutely summable, right? Absolutely summable means all the sample values in the impulse response, right? If you take the summation of those, you should have the finite value that is less than infinity. You should have some finite value. Then only you can say the discrete LTI system is a stable system. That is summation k is equal to minus infinity to plus infinity, magnitude of h of k, absolute value of h of k, right? So if I substitute k is equal to minus infinity means h of minus infinity, h of minus 5, h of minus 4, h of minus 1, h of 0 plus h of 1, h of 2. If you add all these values, you should get the finite value, which is less than infinite. Similarly, a continuous time LTI system is stable only if its impulse response h of t is absolutely integrable, right? Because it is a continuous time signal or continuous time LTI system, you cannot consider the summation here. You have to consider the integration, and this integration has to be absolutely integrable, right? And when you integrate this one, you have to get the finite value. Then only we can say the LTI, continuous time LTI system, is stable, otherwise it is unstable, right? So let us see one example. H of t is equal to 3 times the delta of t. It's a very simple. And in the next video, we are going to discuss more examples on these three properties. So here h of t is given, that is 3 times delta of t. So now we have to determine whether this system is stable or not. So how, since it is impulse response of a continuous LTI system, and this impulse response should be absolutely integrable, then only you can say this system is stable. So how to check this one? So condition is minus infinity to infinity, integration from minus infinity to infinity, magnitude of or absolute value of h of tau into d tau, integration from minus infinity to plus infinity, and h of tau is given, h of t is given 3 into delta of t. So in the expression we have h of tau, so just replace t by tau. So this becomes 3 times delta of tau into d tau. And we know that this delta of tau is equal to 1 at t tau is equal to 0, right? Therefore, delta of tau is equal to 1, 1 into 3 is 3. So 3, which is less than infinity, it is a finite quantity. Therefore, the system is stable, right? So this is about the three system properties of the LTI system in terms of its impulse response, either h of t or h of n. In the next video, we'll be discussing about the step response of the LTI system, and we'll also solve a few examples on these three properties.